There's a photograph taken from space that shows Earth as a pale blue dot suspended in a sunbeam. When astronauts first saw our planet from the moon, many wept. Not from sadness, but from a sudden understanding that everything they knew, every face, every fear, every triumph, existed on that fragile sphere hanging in the darkness. We live our lives believing Earth is vast. We cross continents and call them journeys. We look at oceans and feel their endlessness. But what if I told you that this feeling of vastness is just a whisper compared to what lies beyond? This isn't a story about astronomical measurements or scientific formulas. This is about perspective. About standing in your backyard and realizing that the ground beneath your feet is moving through something so immense that even our largest concepts begin to crumble. We're going to take a gentle journey outward, step by step, breath by breath. We'll watch Earth grow smaller, not through numbers, but through feeling. By the end, you'll understand not just how small Earth is, but what that smallness truly means. Let's begin where all journeys start, at home. Close your eyes and picture Earth from where you're sitting right now. Maybe you're in a room with walls painted a familiar color. Maybe there's a window nearby where light filters through. Outside that window, there's a street. Beyond that street, a neighborhood. Beyond that, a city or town or stretch of countryside. This is your world. The world you touch. The world that touches you back. Earth feels solid because you can press your hand against it. It feels permanent because it was here before you arrived and will remain after you leave. Every morning, the sun rises from the same direction. Every night, stars appear in patterns your ancestors recognized. There's a rhythm to this place that makes it feel like the center of everything. Think about the oceans. If you've ever stood at the edge of the sea, you know that feeling. The horizon stretches so far that it curves away from your vision. The water moves in endless patterns, each wave different from the last. You could sail for days and still see nothing but water in every direction. That ocean feels infinite when you're standing in it. Think about mountains. Some peaks take days to climb. They rise so high that the air thins and breathing becomes an effort. From the summit, you can see for miles forests like carpets, rivers like silver threads. Standing there, you feel you've conquered something vast. Think about forests. Walk into an old forest and you'll find trees that were alive before your grandparents were born. The canopy blocks the sky. You can walk for hours and see nothing but trunks and shadows and the same filtered light. That forest feels like its own world. And cities. Cities sprawl in every direction. Millions of people moving through countless streets. Buildings stack upward like artificial mountains. At night, lights scatter across the landscape like fallen stars. From an airplane window, a city looks endless glowing web that seems to have no edge. This is the Earth we know. The Earth of birthplaces and favorite spots. The Earth where every rock and river has a story. Where every season brings familiar changes. Where the smell of rain means something specific. Where home is not just a location, but a feeling woven into geography. We've mapped this Earth. We've named its parts. 7 continents, each with its own character. Africa, where humanity first opened its eyes. Antarctica, a frozen desert at the bottom of the world. Asia, stretching across so many climates that a single country can contain jungles and tundra. Europe, dense with history and bordered by seas. North and South America, twin landmasses connected by a narrow bridge. Australia, an island continent with creatures found nowhere else, and thousands of small islands scattered between them like punctuation marks. We've measured the distances too. The circumference of Earth at the equator, about 25,000 miles. If you could walk without stopping, it would take you more than a year to circle it. If you could drive non-stop, it would take weeks. These distances feel substantial because they're measured against our lifetimes. The deepest parts of the ocean plunge 7 miles below the surface. At those depths, the pressure would crush a human body instantly. We've sent fewer people to the deepest ocean trenches than we've sent to the moon. That depth feels profound because it represents a place we can barely touch. The highest point on land rises just over 5.5 miles above sea level. Mount Everest, where the jet streams blow and climbers carry oxygen to survive. The mountain kills some who attempt it. That height feels monumental because it pushes against the limits of what our bodies can endure. Between the ocean floor and the mountain peak, there are 12 miles of vertical space. In that thin layer, everything we've ever known has happened. Every civilization, every war, every love story, every discovery, every birth and death. All of human history compressed into a space you could drive through in 10 minutes if the road went straight up. But Earth feels bigger than that. It feels bigger because we experience it horizontally, not vertically. We cross it in journeys that take time. We see its variety: deserts and rainforests, tundras and grasslands, coral reefs and underground caves. Each landscape feels distinct, requiring different words to describe it. At night, we see lights. From space, cities glow. Highway networks draw bright lines across continents. Fishing boats dot the oceans with scattered points of light. Oil rigs burn gas in controlled fires that look like tiny stars. Airports pulse with landing paths. All this light is human presence saying, "We are here." The atmosphere above us holds weather. Clouds form patterns: wispy cirrus at high altitudes, puffy cumulus in afternoon skies, dark cumulonimbus that bring thunder. Hurricanes spiral across oceans with eyes you can see from satellites. Dust storms turn the sky orange. The northern and southern lights paint curtains of green and purple across polar skies. This atmosphere feels thick with activity. We've given names to winds. Trade winds that sailors relied on. Monsoons that bring seasonal rain. The jet stream that pilots ride to save fuel. Chinooks that warm mountain valleys. Each wind has a personality, a predictable behavior that becomes part of regional life. We've marked the planet with borders, though the planet itself shows none. We've decided that certain rivers or mountain ranges or arbitrary lines of latitude separate one group of people from another. We've drawn maps that show these divisions in different colors, as if the land itself changes when you cross from one nation to another. But beneath those invented borders, Earth is continuous. Plate tectonics shift continents at the speed fingernails grow. Earthquakes remind us that the ground isn't as solid as it seems. Volcanoes bring molten rock from below, creating new land while destroying what was there before. The planet is alive in a geological sense, breathing and shifting on timescales that outlast human civilizations. Earth has been here for more than 4.5 billion years. If you compress that time into a single year, humans would appear just minutes before midnight on December 31st. All of recorded history, the pyramids, the Roman Empire, the Renaissance, the Industrial Revolution, everything would fit into the last few seconds before the year ends. Yet, in our brief moment, we've transformed this planet. We've cleared forests and dammed rivers. We've dug mines miles deep and built structures that scrape the sky. We've split atoms and spliced genes. We've created materials that will outlast us by thousands of years. We've changed the composition of the atmosphere itself. In geological terms, we've done all this in an instant, but to us, it feels like the entire story. This is Earth as we know it. This is the world that feels complete and whole. The world where distance means something because it takes effort to cross. The world where the ocean seems endless because you can't see the other shore. The world where mountains feel permanent because they don't move in a human lifetime. Hold on to that feeling. Remember how vast Earth seems when you're standing on it. Remember how a single country can take days to cross. Remember how the ocean stretches beyond what your eyes can hold. Remember how forests feel like labyrinths. Remember how cities seem infinite when you're walking their streets. Because now we're going to step back. Just a little, just enough to see Earth not from its surface, but from above. And something changes when you do that. Something fundamental shifts when you stop being on Earth and start being away from it. The planet that felt infinite suddenly has edges. The world that seemed endless suddenly looks contained. And that's just the beginning. Imagine you could rise straight up from where you're sitting. Not fast. Not like a rocket launch. Just a slow, steady ascent. A gentle lifting that takes you higher than any bird has ever flown. At first, everything below you stays familiar. Buildings get smaller but remain recognizable. You can still pick out roads and parks. Colors stay vivid. If you look down from a tall building, this is what you'd see. The world is still detailed, still personal. Keep rising. Now you're higher than commercial airplanes fly. The ground below starts to lose its texture. Individual trees blur together into green patches. Roads become thin lines. Cities flatten into organized grids of light and shadow. You can no longer see people. You can no longer see cars moving. What was once intimate becomes abstract. The sky around you is darkening. Not because the sun has set, but because there's less air to scatter its light. The blue that seemed infinite from the ground is actually thin. You're passing through it. The atmosphere isn't a thick blanket. It's more like a coat of paint on a basketball. This is the strange truth of Earth's atmosphere. It feels substantial when you're breathing it. It carries clouds and birds and pollen. It brings wind and rain. It holds the pressure that keeps your blood from boiling. From the ground, the sky seems limitless. But it isn't. It's a delicate layer clinging to a rocky sphere. Half of the atmosphere's mass exists below 18,000 feet. That's lower than some mountain peaks. If you could slice Earth like an apple, the atmosphere would be thinner than the apple's skin. Stand at sea level and look up. The air you can actually breathe exists in a zone you could drive through in a few minutes if the road went vertical. Keep ascending. You're now in the realm where only specialized aircraft can reach. The air is so thin that ordinary engines can't find enough oxygen to burn fuel. Human lungs couldn't extract enough oxygen to stay conscious. The temperature is dropping fast. Outside your imaginary vehicle, it's well below freezing, even if the ground below is experiencing summer heat. Look down now. Earth is beginning to curve. This is the moment that changes everything. When you're on the surface, the planet seems flat because you can only see a tiny portion at a time. Your horizon is limited by how far light can travel before the curve of Earth blocks it. But up here, you can see that curve. You can see the edges where the land meets something else, black of space. The atmosphere is visible now as a layer, a thin blue line between the solid planet and the infinite darkness above. It glows softly, lit by the sun from an angle that you never see from the ground. This glow is called the air glow. It's created by chemical reactions in the upper atmosphere. From here, you can see that the air isn't uniform. It has structure. Layers of different density catch light differently. At this height, maybe 60 miles up, you're technically in space. But you can still see the atmosphere below you. It hasn't ended. It's just become too thin to scatter much light. Satellites orbit above this, but they still experience atmospheric drag. Over time, even in this near vacuum, they slow down and eventually fall back to Earth. Space doesn't start suddenly. It's a gradual thinning, like how a beach slowly becomes ocean. Look at Earth from here. It's no longer where you are. It's where you were. The planet is below you now, separate. You can see multiple countries in a single glance. Weather systems sprawl across entire continents. A hurricane that would dominate the news on the ground looks like a white spiral, beautiful and terrible at once, spinning slowly over an ocean. The continents are recognizable. If you know your geography, you can name them. But they don't look like maps. They look like shapes on a sphere. Mountains don't stand out. Borders don't exist. Cities, even the largest ones, are barely visible except at night when their lights cluster in bright patches. During the day, most human infrastructure disappears. What you see instead is green where forests grow, brown where deserts stretch, white where ice persists, blue where water covers everything else. The blue dominates. Oceans make up more than 70% of Earth's surface. From this height, you understand why early sailors feared them. They extend in every direction. If you were to fall from here into the Pacific Ocean, you could land 1,000 miles from any shore. The water that seems so local when you're standing beside, it is actually a connected system wrapping around the entire planet. But even more than the blue of water, there's the blue of atmosphere. That thin shell is what makes Earth different from every other planet we've observed. It's the reason there's life here. It filters the sun's harshest radiation. It burns up most meteors before they reach the ground. It distributes heat from the equator to the poles. It holds the water vapor that becomes rain. It carries sound so you can hear voices and music and thunder. Without it, Earth would be as silent and dead as the moon. The surface temperature would swing from scorching when facing the sun to freezing when turned away. There would be no wind, no weather, no blue sky, just rock and regolith under black emptiness. The fragility is obvious from here. This shell of air that enables everything is thinner than the skin of an onion. You could punch through it in a matter of minutes if you could fly straight up. It's held in place only by Earth's gravity. It can't escape into space, but it's not thick either. It's a compromise between forces, enough to be useful, but barely, and it's temporary. Not in human terms. The atmosphere will outlast our civilizations. But in cosmic terms, it's a fleeting thing. Mars once had a thicker atmosphere. Venus' atmosphere became toxic. Earth's atmosphere is breathable because of a precise balance of factors that won't last forever. The sun is slowly brightening. Eventually, billions of years from now, Earth's oceans will boil away and the atmosphere will change. This blue shell is a moment in the planet's life, not a permanent feature. From this height, you can see clouds casting shadows on the ground. Those shadows are hundreds of miles long. A storm system that seems local from below is revealed as part of a larger pattern. Clouds form lines where air masses collide. They spiral around low-pressure zones. They cluster over mountains where air is forced upward. The atmosphere isn't just sitting there. It's churning constantly, redistributing energy, trying to balance temperatures that the sun keeps unbalancing. You can see the terminator now, the line between day and night sliding across the planet. It doesn't move like sunset feels from the ground. From here, the shadow moves fast, sweeping across the surface at 1,000 miles per hour at the equator. Cities disappear into darkness and their lights click on. The transition is sharp because the atmosphere is too thin to scatter much light once the sun dips below the horizon. At the poles, the atmosphere does something special. Charged particles from the sun follow Earth's magnetic field lines and crash into air molecules, making them glow. The auroras. From the ground, they're curtains of light dancing across the sky. From here, they're glowing rings around the polar regions, green and occasionally red, pulsing with the rhythm of solar wind. The atmosphere protects Earth from that wind. Without it, charged particles would strip away water and sterilize the surface. Mars lost most of its atmosphere billions of years ago, and the solar wind has been scouring its surface ever since. Earth's magnetic field helps, but the atmosphere is the main shield. A shield you could drive through faster than your morning commute. Look at the limb of Earth, the edge where the planet curves away. The atmosphere makes a visible gradient. Near the surface, it's opaque with weather. Higher up, it becomes translucent. Higher still, it's just a faint glow. Then nothing. Just the blackness of space and the hard light of stars that don't twinkle anymore because there's no air to disturb their light. This is the shell we live inside. This is the container for everything we've ever called home. Every breath you've ever taken came from this thin layer. Every gust of wind that's ever blown, every cloud that's ever formed, every raindrop, every snowflake, all contained in a zone so narrow that if Earth were the size of a basketball, the atmosphere would be thinner than a sheet of paper wrapped around it. And we're changing it. From here, you might see smoke from wildfires, brown smudges of pollution over industrial regions. The slow creep of desertification. Changes that happen faster than the planet's natural rhythms. The atmosphere isn't just a passive shell, it's a mixture of gases in a specific balance. Add too much of one gas and the balance shifts. The temperature changes. Weather patterns shift. Ice melts. Seas rise. The fragility you see from up here isn't just visual, it's real. But don't let that overshadow the beauty. Because from this height, Earth is beautiful. The swirls of white clouds against blue water, the greens and browns of land, the shimmer of sunlight on ocean waves, creating patterns that shift like living things. The thin crescent of atmosphere glowing at the edge. No other planet we've seen looks like this. None have this color. None have this delicate balance between rock and water and air and life. Hold on to this image, Earth wrapped in its fragile shell. Still whole, still detailed enough to recognize. Still home, just seen from a distance. Because now we're going to move farther away, and that thin blue line is about to become even thinner. Keep drifting away from Earth, not quickly. There's no rush here. Let the planet shrink slowly beneath you. The curve becomes more pronounced. The atmosphere becomes a barely visible outline. Details blur into textures. Continents become obvious shapes you recognize from globes. You're moving into the space between Earth and its companion, the Moon. That familiar presence that you've seen countless times in the night sky. The object that pulls the oceans into tides. The only other world humans have walked on. But space is already changing what you see. Earth is bright, painfully bright. The sun illuminates it fully from this angle, and clouds reflect light like mirrors. The planet almost glows against the darkness. Looking at it too long would hurt your eyes. It's strange how something so vivid can exist in such emptiness. Because the emptiness is the first thing you notice out here. It's not like the space between objects on Earth. It's not air with nothing in it. It's nothing. Perfect nothing. No molecules to carry sound. No atmosphere to scatter light. Just void. The distance between Earth and the Moon is about 240,000 miles. That number is hard to grasp, so think of it this way. You could fit 30 Earths side by side in the space between Earth and Moon. That distance feels wrong somehow. From Earth, the Moon looks close. You can see its features with your naked eye. The dark Maria, ancient lava plains. The bright highlands, old, cratered terrain. It looks like you could reach up and touch it, but you can't. It's so far away that light takes more than a second to travel between Earth and Moon. Radio signals sent from Earth to astronauts on the Moon had a noticeable delay. Questions and answers separated by silence. As you drift toward the Moon, Earth begins to look like the Moon looks from Earth. It goes through phases. When you're on the side of the Moon facing the Sun, you'd see Earth nearly full, a bright blue and white marble hanging in the black. When you're on the side of the Moon facing away from the Sun, Earth becomes a crescent, just a sliver of illuminated edge against darkness. This is the dance they do. Earth and Moon locked in gravitational embrace. The Moon doesn't orbit Earth exactly. They both orbit a point between them called the barycenter. Because Earth is so much more massive, that point lies inside Earth, but not at its center. They're partners, not a parent and child. They pull on each other constantly. That pull is gentle but relentless. The Moon tugs on Earth's oceans, creating bulges of water on the sides, facing and opposite the Moon. As Earth rotates beneath these bulges, coastlines experience high and low tides. The rhythm of tides has shaped life in the oceans. Creatures evolved to match these patterns. Humans built calendars around them. But the Moon pulls on more than water. It tugs on the solid Earth too. The ground beneath your feet rises and falls by several inches each day due to lunar gravity. You can't feel it because everything around you rises and falls together, but it happens. The planet flexes. This flexing creates friction inside Earth, generating heat. Over billions of years, this friction has slowed Earth's rotation. Days are getting longer. Imperceptibly longer. A day on early Earth was only a few hours. The Moon's pull has been stretching it ever since, and the Moon is moving away. The same tidal forces that slow Earth's rotation push the Moon into a higher orbit. It moves away at about 1.5 inches per year, the same rate your fingernails grow. In the age of the dinosaurs, the Moon was closer. It looked bigger in the sky. Eclipses were more common. In the distant future, it will be too far away to completely cover the Sun. Total solar eclipses will become impossible. The alignment we have now, where the Moon appears almost exactly the same size as the Sun in our sky, is temporary. Coincidence of timing. Look at the Moon as you approach it. Unlike Earth, it's not blue. It's grey and tan and brown. Ancient. Weathered. But not by weather. By impacts. Billions of years of asteroids and comets crashing into a surface with no atmosphere to burn them up first. Each impact left a crater. The surface is saturated with them. Craters inside craters. Layers of destruction reaching back to the solar system's violent youth. The largest impacts created the Maria. Those dark patches visible from Earth, they're not seas, despite their name. Their basalt plains formed when impacts cracked the Moon's crust and lava flooded the basins. The lava cooled and froze billions of years ago. It's been solid ever since. Nothing moves on the Moon. No wind to erase tracks. No rain to wash away scars. Footprints left by Apollo astronauts in the 1960s are still there, perfectly preserved. They'll remain for millions of years. The Moon has no atmosphere. No blue shell like Earth. Nothing to soften the harshness of space. During the lunar day, which lasts about 2 Earth weeks, surface temperatures soar to over 200 degrees Fahrenheit. During the lunar night, equally long temperatures plunge to nearly minus 300 degrees. There's no air to distribute heat. No buffer against the sun's radiation. Standing on the moon, you'd see stars during the day because there's no atmosphere to scatter sunlight and make the sky blue. From the moon's surface, Earth hangs in the sky. It doesn't rise or set like the moon does from Earth. Because the moon is tidally locked, always showing the same face to Earth, our planet stays in roughly the same position in the moon's sky. It goes through phases, but it doesn't move across the sky. If you're on the near side of the moon, Earth is always visible. If you're on the far side, you never see it, ever. That far side of the moon is often called the dark side, but that's misleading. It gets just as much sunlight as the near side. It's dark to us because we never saw it until spacecraft went around the moon and photographed it. It looks different from the near side. Fewer Maria, more highlands, heavily cratered, older. The reason for the difference is still debated. Maybe Earth's gravity affected how impacts occurred. Maybe it influenced volcanic activity. The asymmetry is a mystery written in rock. The moon has no magnetic field now, but it once did. Ancient rocks show magnetization from billions of years ago. Something inside the moon was molten and churning, creating a magnetic dynamo like Earth's. But the moon is smaller. It cooled faster. The dynamo died. Now there's no protection from solar wind. Particles from the sun hit the surface directly, slowly eroding it into fine dust. That dust is everywhere. It's not like sand on Earth. It's sharp because there's no wind or water to round the grains. It's electrostatically charged from solar radiation. It clings to everything. Apollo astronauts found it got into every seal and joint of their equipment. Smelled strange, like gunpowder, some said. It's made of microscopic glass beads created by meteor impacts flash melting rock. Look back at Earth from the moon. You're now about 250,000 miles away. Earth looks small. Not tiny yet, but small enough to block out with your thumb if you held your hand at arm's length. That world that felt infinite is now something you can obscure with a small gesture. But it's still bright, still vivid, still alive with color. Blue oceans, white clouds, brown and green land. It's the only colored object in a black void dotted with white stars. Everything else is grayscale. The moon beneath your feet, the stars around you. Even the sun is white from here because there's no atmosphere to make it look yellow. Earth is the only source of color in this part of space. You can't see individual countries from here. You can't see cities except as faint smudges of light on the night side. You can't see roads or buildings or forests as distinct things. You see cloud patterns and continent shapes and ocean expanses. Earth has become a portrait, not a landscape. A whole, not a collection of parts. The pull between Earth and Moon is invisible, but you can feel it conceptually. They're bound together, not touching, but never separate. The space between them is empty, but it's not neutral. It's threaded with gravity. Each world feels the other's presence constantly. This connection has existed for more than 4 billion years. The moon probably formed when a Mars-sized object struck early Earth, sending debris into orbit that eventually coalesced. If that's true, the moon is made partly of Earth. They're fragments of the same collision, forever circling each other. This relationship stabilizes Earth. The moon's gravity keeps Earth's axial tilt steady. Without it, Earth's axis would wobble chaotically over millions of years. The climate would swing wildly. Seasons would become unpredictable. Life would have evolved differently, if at all. The moon is a guardian, a quiet presence that keeps Earth livable. From this distance, you can see both objects at once. Earth and moon together, a system. From the moon, Earth goes through a full cycle of phases every month. New Earth, crescent Earth, half Earth, gibbous Earth, full Earth, and back, each phase showing a different portion illuminated by the sun. During a full Earth, the moon is between Earth and the sun. From Earth's perspective, this is a new moon. During a new Earth, the moon is on the opposite side of Earth from the sun. From Earth's perspective, this is a full moon. They mirror each other in reverse. Eclipses happen when the alignment is perfect. When the moon passes through Earth's shadow, you see a lunar eclipse from Earth. The moon turns red because Earth's atmosphere bends red sunlight into the shadow. When the moon passes between Earth and sun, you see a solar eclipse from Earth. The moon blocks the sun perfectly, revealing the sun's corona. These events are rare because the moon's orbit is tilted slightly. Most months, the alignment isn't quite right. But when it is, the sky performs a show humans have watched with wonder and fear for all of history. Hold this image, Earth and moon separated by emptiness. Two worlds linked by invisible forces. One living and vibrant. One dead and grey. One wrapped in air and water. One exposed and silent. Together they're a system, but separate their illustrations of different fates. Earth got lucky. It's the right size to hold an atmosphere. It's the right distance from the sun to have liquid water. It has a moon that stabilizes it. Remove any of these factors, and it might look like the moon, barren, silent, unmarked by life. But we're not done stepping back. From the moon, Earth is still visible, still recognizable, still obviously important. Now we're going to move farther, into the darkness between worlds, and Earth is about to stop being special. Continue outward, past the moon's orbit, into the space between planets. This region has a name, Silnur space, but that's just the beginning. Beyond the moon's orbit, you enter interplanetary space, the realm of the solar system proper. The first thing you notice is how quickly Earth begins to fade. Not because it's moving away from you, you're moving away from it, but because something brighter dominates your view, the sun. It's no longer a comforting presence in the sky. It's the sky. A blazing sphere of light, so intense that you can't look directly at it. Everything else becomes secondary. Earth is still visible. A bright spot trailing behind you. Still blue. Still distinct. But it's competing now. Competing with the overwhelming luminosity of the star that gives it warmth. From this distance, maybe 1,000,000 miles from Earth, the planet has begun to look like just another object in space. A satellite of the sun, which is the true center of this system. The sun's light floods everything. There's no atmosphere out here to make the sky blue. The sky is black. But it's a black filled with the sun's harsh radiance. Stars are still visible, but they're harder to see. Your eyes have to adjust away from the sun's direction to notice them. The sun drowns out everything nearby with pure brightness. Earth is getting smaller. Imagine holding a marble at arm's length. That's roughly how big Earth appears from a few million miles away, still clearly a sphere. Still showing weather patterns if you look carefully, but diminishing. The moon is no longer visible unless you know exactly where to look. It's too small, too dim, too grey. It's vanished into the glare. Keep moving. You're heading generally outward now, away from the sun. Not toward anything specific, just away. Giving yourself distance. As you go, Earth continues to shrink. The details wash out. Continents blur together. The blue becomes a general impression rather than a specific color. You can still tell it apart from the blackness, but barely. At 10 million miles, Earth is a dot. A pale blue dot, as the famous photograph would later be titled. But even that description is generous. It's more of a pixel, a single point of light that could be anything. You'd only know it's Earth if someone told you. Otherwise, it's indistinguishable from a distant star. This is where light starts to betray distance. The light you're seeing from Earth is old, not ancient, but delayed. It left Earth seconds or minutes ago, depending on how far you've traveled. You're not seeing Earth as it is now. You're seeing Earth as it was when that light began its journey. This delay becomes important later. In deep space, light is always a messenger from the past. The sun is still overwhelming. Even from tens of millions of miles away, it's a disk. A visible circle with edges. It's smaller than it appears from Earth, but still obviously a sphere, not a point. Its light is undiminished by distance because space is empty. There's nothing to absorb or scatter the light. It travels in straight lines at constant brightness until it hits something. Other planets are starting to become visible. Not because you're closer to them, because you're in a position to see them against the darkness instead of against the sun's glare. Venus, the brightest, shines like a beacon. It's closer to the sun than Earth, so from your position farther out, Venus appears near the sun. A brilliant white star that doesn't twinkle. Mars, farther out than Earth, is visible too. A reddish point. Dimmer than Venus but unmistakable in color. These are Earth's neighbors. But neighbors is a misleading word. The distances between planets are staggering, empty beyond comprehension. If Earth is a marble, the space to the next planet isn't measured in feet or miles. It's measured in millions of miles. And that's just to the nearest one. Venus orbits about 25 million miles closer to the Sun than Earth. Mars orbits about 50 million miles farther from the Sun than Earth. But their orbits are elliptical, not circular. Sometimes they're closer to each other, sometimes farther. At their closest approach, Earth and Mars are about 35 million miles apart. At their farthest, more than 250 million miles separate them. These are the planets we call neighbors. Between Earth and Mars, there's nothing, no markers, no signposts, just void. Sunlight crosses it. Gravity from the sun pulls on objects within it, but matter is sparse, a few asteroids, dust, the occasional comet, but mostly nothing. You could travel for millions of miles and never encounter anything larger than a grain of sand. This emptiness is the solar system's defining characteristic. Planets are rare. Are tiny islands of matter separated by oceans of vacuum. We teach children the solar system with diagrams showing planets in a line, but those diagrams are lies of scale. If you drew the solar system to scale with Earth, the size of a peppercorn, the Sun would be a beach ball 8 feet across. Mercury would be another peppercorn 10 yards away. Venus would be a slightly larger peppercorn 20 yards from the Sun. Earth would be at 26 yards, Mars at 40 yards, and then nothing for 100 yards until you reach Jupiter. But from where you're drifting now, none of this scale feels real yet. Earth is still visible. Small but present. The Sun is still a disk. You're still in the inner solar system where things feel relatively close. Where planets orbit in years, not decades. Turn around. Look back toward the Sun. Earth is lost in the glare now, unless you block the Sun with your hand. Hold up your palm. Create a shadow. In that shadow, you might catch a glimpse of Earth. A tiny blue spark. Fragile. Temporary. 1 second it's there. The next, you've moved your hand and the sun's brilliance washes it out. This is what the Voyager spacecraft saw when it took the famous pale blue dot photograph in 1990. From beyond Neptune, more than 4 billion miles away, Voyager turned its camera back toward the sun. Earth appeared as a single pixel suspended in a beam of scattered sunlight. Carl Sagan wrote about it. How that pale blue dot contained everyone you've ever known, every human who has ever lived, every joy and suffering, every civilization, every war and peace, all compressed into a point of light barely visible against the vastness. But you're not that far yet. You're still close enough to see Earth without special instruments. It's just hard. It's hard because the sun dominates. The sun is the center, and everything else is peripheral. Earth orbits at an average distance of 93 million miles from the sun. We call this distance an astronomical unit, 1 AU. It's a unit of measurement used for distances within the solar system because the numbers get unwieldy otherwise. From your current position, maybe 50 million miles from Earth, the sun is closer than Earth is to the sun. You're still deep in its gravitational well. The pull toward the sun is noticeable. If you weren't moving, you'd fall inward. Everything in the solar system is falling toward the sun constantly. The trick is to move sideways fast enough that you keep missing it. That's what an orbit is, a continuous fall that never ends because you're also moving laterally. Earth is falling around the sun at about 67,000 miles per hour. That speed is hard to conceptualize, but it's necessary. Any slower and Earth would spiral inward. Any faster and it would escape, determined by the sun's mass and Earth's distance. Every planet has its own required speed. Mercury races at over 100,000 miles per hour. Neptune drifts at just over 12,000. The farther from the sun, the weaker its pull and the slower you need to move to maintain orbit. From here, you can see the solar system not as a collection of places, but as a structure. A star surrounded by orbiting debris. The planets are the largest pieces, but they're rare exceptions. Most of the debris is small. The asteroid belt between Mars and Jupiter contains millions of rocks. But if you added up all the asteroids, their total mass would be less than Earth's moon. The belt isn't dense, it's sparse. You could fly through it without seeing a single asteroid nearby. Beyond the planets, farther than you can see from here, are more structures. The Kuiper belt, where icy objects orbit in the outer darkness. The Oort cloud, a theoretical shell of comets surrounding the entire solar system at distances so great that the sun appears as just another star. These regions mark the edge of the sun's influence. Beyond them is interstellar space, the realm between stars. But those distances are still unimaginable from here. Right now, Earth is your reference point, and it's vanishing. Look for it again, there. A faint bluish point, barely distinguishable from background stars. If you didn't know where to look, you'd miss it. The world where you were born. The world where every person you've ever known lives. The world that contains every story and song and monument. Reduced to a pixel. The sun hasn't gotten dimmer, but Earth has. That's the asymmetry of luminosity. The sun produces light, Earth reflects it. As you move away from Earth, the light it reflects becomes fainter. As you move away from the sun, it still shines just as bright for millions more miles. The sun is the constant. Everything else fades first. Other stars are becoming more prominent in your vision. Not because they're getting brighter, but because your eyes are adjusting. When you were near Earth, the sun was behind you or to the side. Now you're in a position where the sun is one object among many, It's still the brightest by far. But Sirius, the brightest star in Earth's night sky, is visible. So are Canopus, Regal, Betelgeuse. Constellations that humans have named are scattered around you. Orion, the Big Dipper, the Southern Cross. From here, they look the same as they do from Earth. You haven't traveled far enough to distort them. Those stars are so distant that moving millions of miles means nothing to them. Sirius, the closest bright star, is about 8 light years from the Sun. That means light takes 8 years to travel from Sirius to here. 8 years, at the speed of light. The distance is so vast that the fastest spacecraft humans have built would take tens of thousands of years to reach it. But you're not looking at Sirius. You're looking back at Earth, trying to find it. Trying to hold on to the sense that it matters. And it does matter. It matters to you. But the universe doesn't acknowledge that. The universe treats Earth the same way it treats every other rock, indifferently. From this distance, Earth's significance is not inherent, it's projected. You care because you came from there. But nothing about Earth's appearance demands attention. The moon is completely gone now. Invisible, too small and too dark. It's still there, still orbiting Earth, still pulling tides and stabilizing the axis. But from here, it's erased, irrelevant. A detail too minor to perceive. Earth will disappear soon too, not because it's moving, because you are. Every mile you travel outward makes Earth fainter. The light it reflects spreads across a wider area. The inverse square law is relentless. Double the distance, and the brightness becomes 1/4. Triple the distance, and it becomes 1/9. There's no way around this. Light spreads. Objects dim. Eventually, they vanish. Hold on to the memory of Earth as something you could see. Something with color and shape, because now we're going deeper into the solar system. And Earth is about to become just another piece of the past. Another object left behind in the journey outward. Another thing that was once everything, now fading into the background of something much larger. Drift farther. There's no sound. There's never sound out here. Sound needs molecules to vibrate through. Out here, there's almost nothing. Vacuum. Not perfect vacuum. Space is never truly empty, but close enough. A few atoms per cubic centimeter. Mostly hydrogen. Remnants of the solar wind. Traces of dust. But functionally, it's nothing. The silence is absolute. If a planet exploded in front of you, you wouldn't hear it. There'd be light, a sudden flare, and then debris expanding outward. But no thunder, no roar. Just silent destruction. This emptiness is the true nature of space. Not the dramatic swirling nebulas or busy asteroid fields that movies show. Just void. Calm, unchanging. You're somewhere between Earth and Mars now, though those reference points are becoming meaningless. Both are too far to see clearly. Earth might be a faint star behind you. Mars might be a faint star ahead. Or maybe you can't see either. Maybe they're lost against the background of other stars. This is the space that defines the solar system, not the planets. The space between them. Think about cathedrals. Old stone cathedrals with high vaulted ceilings. When you stand inside one, you feel the space above you. It presses down in a way, not with weight, but with presence. The empty air is part of the architecture. The silence between sounds is part of the music. The solar system is like that, but unimaginably larger. The planets are like candles scattered across a dark cathedral floor, each one a point of light. each one tiny against the enormity of the empty space around it. If you could somehow place the planets side by side, all 8 major planets touching, they'd span less than 250,000 miles. That sounds like a lot until you remember that Jupiter alone is about 88,000 miles wide. The planets are real. They're substantial, but the space between them makes them irrelevant. Neptune orbits nearly 3 billion miles from the Sun. If you lined up planets from the Sun to Neptune, you'd run out of planets after a tiny fraction of the distance. The rest would be empty room, unfilled space, void extending in every direction. This void isn't hostile. It's not pulling you apart or crushing you. It's just absent. There's no weather here. No wind. No temperature fluctuations because there's no atmosphere to hold or move heat. Objects in space are whatever temperature the balance between absorbed sunlight and radiated heat determines. On the side facing the Sun, things get warm. On the side facing away, things get cold. But there's no medium to transfer that temperature, no air to chill your skin. In vacuum, heat transfer happens only through radiation, slow and inefficient. Dust exists out here, but it's sparse. Microscopic grains scattered across millions of miles. Occasionally, these grains collide with something and vaporize. Occasionally, they clump together over millions of years and form larger objects, but mostly they drift. Particles that might be fragments of ancient comets, bits of asteroids ground down by impacts. Debris from the solar system's formation 4.5 billion years ago. That formation was violent. A cloud of gas and dust collapsed under its own gravity. The center became dense and hot, eventually igniting nuclear fusion. The Sun was born. The leftover material formed a disk around it. Within that disk, particles collided and stuck together. Dust became pebbles. Pebbles became rocks. Rocks became boulders. Boulders became planetesimals. Planetesimals became planets. The process took tens of millions of years. It was messy. Objects smashed together. Some merged. Some shattered. The survivors are what we call the solar system. But most of the disk is gone now, swept up by planets or ejected into interstellar space or fallen into the Sun. What remains is this sparse collection of objects separated by vast distances. The solar system isn't full. It's empty with occasional interruptions. Imagine throwing a handful of sand into a cathedral. Each grain represents a piece of matter in the solar system. The space between grains represents the void. That's the ratio. Not even sand in a cathedral. More like a dozen grains scattered across a city. That's how empty space is. Light crosses this emptiness constantly. Photons from the Sun radiate outward in all directions. Some hit planets. Most don't. They travel forever until something stops them. Some photons that left the Sun minutes ago will travel for millions of years before encountering anything. The solar system is transparent. Light passes through it unobstructed. But light from the Sun gets weaker with distance. Not because the light itself changes, but because it spreads. Imagine a flashlight. Close to the bulb, the light is concentrated. Farther away, it spreads into a wider circle. The total amount of light is the same, but it's distributed over a larger area. The same principle applies to the Sun. At Earth's distance, sunlight delivers a certain amount of energy per square meter. At Mars's distance, it's less than half. At Jupiter's distance, it's less than 4%. At Neptune's distance, it's 0.1%. This dimming changes everything. On Earth, sunlight is intense enough to warm the surface and drive weather. On Mars, it's weaker. Thin atmosphere. Cold surface. On Jupiter, Sunlight barely matters. The planet radiates more heat from its interior than it receives from the sun. On Neptune, the sun is just a bright star. It provides some light, but not much warmth. The outer planets are cold, not because they're made of different materials, but because they're so far from the sun that its warmth is negligible. You're still in the inner solar system though. Still where sunlight feels real. Still where the sun is a visible disk, not just a point. Mars orbits at about 1.5 AU from the sun. From Mars, the sun appears about half the size it does from Earth. Still clearly a disk. Still obviously the sun, but smaller. Mars itself is a strange world, red because its surface is rich in iron oxide. Rust. Ancient river valleys suggest water once flowed there. Polar ice caps grow and shrink with the seasons. Dust storms can engulf the entire planet. It's a dead world now, but it might have been alive once. Maybe. We don't know yet. Rovers are there, digging and analyzing and searching for signs of past life. But from your position in space, Mars is just a reddish point. You can't see the rovers. You can't see the valleys or ice caps. You can't see anything but color and vague shape. The asteroid belt lies beyond Mars. Millions of rocky objects orbiting between Mars and Jupiter. Unchanged. Ancient. Meteorites that fall to Earth are often asteroid fragments. We can analyze them in laboratories, measure their age, determine their composition. They're time capsules from an era before planets fully formed. But from your position, the asteroids are invisible. Too small, too dark. You're seeing the architecture of the solar system, the spacing, the emptiness, the way matter clusters in specific orbits, but not the details. The solar system is defined by absence more than presence. Gravity is still here though. You can't see it, but it shapes everything. The sun's gravity reaches out across billions of miles, holding planets in their orbits. Each planet's gravity creates a sphere of influence where it dominates over the sun's pull. Earth's sphere of influence extends about 600,000 miles, farther than the moon. Inside that sphere, objects orbit Earth. Outside, they orbit the sun. Every planet has a similar sphere. They're islands of local influence in a sea of solar dominance. Gravity isn't uniform either. Planets perturb each other's orbits slightly. Jupiter, the most massive planet, influences everything. Asteroids and comets are nudged by Jupiter's gravity. Some are ejected from the solar system. Some are flung inward toward the sun. Jupiter acts as a cosmic vacuum cleaner, protecting the inner planets from some impacts, but also as a sniper, occasionally redirecting objects toward those same inner planets. Its influence extends far beyond its physical size. You won't see Jupiter yet, not from here. It's too far. Jupiter orbits at about 5 AU from the Sun. That's 5 times farther from the Sun than Earth. In the emptiness of space, the distance is enormous. It takes light over 40 minutes to travel from the Sun to Jupiter. Radio signals sent from Earth to spacecraft at Jupiter have a similar delay. Conversations are impossible. You send a command and wait nearly an hour for a response. But even though you can't see Jupiter, you're in its domain. Its gravity affects everything in the solar system to some degree. Orbits precess slightly because of Jupiter's pull. Resonances form, patterns where orbital periods sync up. Some asteroids orbit the Sun exactly twice for every one Jupiter orbit. Others orbit exactly 3 times for every 2 Jupiter orbits. These resonances are stable zones where asteroids cluster, or they're unstable zones emptied by chaotic gravitational interactions. Jupiter sculpts the solar system without touching anything. Look around. The sun is behind you now, maybe. Or to your side. You're no longer falling toward it because you've moved far enough out that your trajectory is different. Or maybe you're still falling, just slowly. Without reference points, it's hard to tell. The stars don't move. They're too far away. Only the planets move noticeably, and they're too faint or too slow to provide a sense of motion. This is the emptiness astronauts describe. Not the view, the feeling. The absence of everything familiar. No up or down, no landmarks, no horizon. Just blackness dotted with stars and the occasional planet. Humans evolved in environments filled with matter. Air, ground, water, trees. Out here, there's nothing to hold on to. Nothing to navigate by except distant points of light. And it's quiet, profoundly quiet. Not the quiet of a library or a forest. The quiet of non-existence. Sound doesn't just fade away. It never exists. Your heartbeat is the only sound. You're breathing. The hum of whatever machine is keeping you alive, if you're lucky. Otherwise, silence. Complete and eternal. This silence makes you realize something. The solar system isn't a place humans were meant to visit. It's not hostile. It's not trying to kill you, but it's indifferent. There's no air because there's no mechanism to hold it. There's no warmth because the sun is far away. There's nothing to eat, nothing to drink, nowhere to stand. Every human who has entered this void has done so inside a metal bubble, carrying a piece of Earth with them. We can't survive out here naked. We can only visit briefly, protected. Yet this emptiness is beautiful in a way. Beautiful because it's pure. There's no pollution, no decay. Nothing rots in vacuum. Objects that enter space stay preserved. The footprints on the moon will outlast human civilization. Spacecraft sent to the outer planets will drift in the darkness long after Earth is gone. This emptiness is eternal. It was here before the solar system formed. It will be here after the sun dies. And we're still in the shallow end. The inner solar system, where planets are close and sunlight is bright. Beyond this is more emptiness, more distance. Planets farther out than you can imagine from here, and beyond those, the true edge of the sun's influence. And beyond that, the stars, but for now, float here. In the quiet between worlds, where Earth is a memory and destination doesn't matter, where time passes but nothing changes. This is the cathedral, and the planets are just dust. Turn toward the sun. Face it directly. Even from millions of miles away, even as a smaller disk than it appears from Earth, it commands everything. This is the heart of the solar system. Not the center in a geographical sense. There's no geography in space, but the center of mass, energy, gravity, light. Everything else is secondary. The sun contains 99.86% of the solar system's total mass. All the planets combined, Jupiter, Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, along with all the moons, asteroids, comets, dust, and everything else, account for less than 1/5 of 1%. The sun isn't just the largest object in the solar system. It's almost the only object. Everything else is a rounding error. From Earth, the sun looks small because we're standing on something solid and surrounded by atmosphere and landmarks. It's just a bright circle in the sky. We glance at it and look away because it hurts. We measure our days by it. It rises and sets, and we barely think about what it is. But out here, Away from Earth, away from context, the sun reveals itself as what it truly is, a star. A sphere of plasma so hot that atoms are torn apart into charged particles. A fusion reactor converting mass into energy, a rate of 4 million tons per second. Every second, the sun consumes 4 million tons of its own mass and converts it into energy. That energy radiates outward as light and heat. It takes about 8 minutes for that light to reach Earth. It takes longer to reach the outer planets, but it's constant, relentless. The sun has been doing this for about 4.6 billion years. It will continue for another 5 billion years before its fuel runs low. The light you're seeing now left the sun's surface minutes ago, depending on your distance. But that light began its journey much earlier. Photons created in the sun's core by fusion reactions can't escape immediately. The sun is too dense. Photons bounce around inside, absorbed and re-emitted countless times. It takes thousands of years for a photon to random walk its way from the core to the surface. Once it reaches the surface, it flies free, traveling through space in a straight line until something stops it. Some of that light is hitting you. Even from tens of millions of miles away, sunlight is intense. There's no atmosphere to filter it, no ozone layer to block ultraviolet, no clouds to soften it. It's raw starlight, and it's dangerous. Prolonged exposure would burn skin, damage eyes, increase cancer risk. This is why spacesuits have reflective visors, why spacecraft need thermal protection. The sun's radiation is harsh because nothing mediates it. But most of the sun's light misses everything. It radiates outward in all directions. The tiny fraction that hits Earth is enough to power all of life, drive weather, warm the oceans. But that's a minuscule portion. Most of the sun's energy flies past Earth into empty space, traveling forever until it hits something or redshifts into invisibility over cosmic distances. The sun isn't just a light source. It's a gravity well. Its mass warps space around it. Imagine a heavy ball placed on a stretched rubber sheet. The sheet curves around the ball. Objects placed on the sheet roll toward the ball. That's a two-dimensional analogy for what the sun does to space. It curves space in all directions. Planets don't orbit because they're on tracks. They orbit because they're moving through curved space, following the straightest possible paths, which happen to be ellipses. Earth's orbit is nearly circular, but not quite. The distance between Earth and Sun varies by about 3 million miles over the course of a year. When Earth is closest to the Sun, perihelion, it's about 91 million miles away. When it's farthest, aphelion, it's about 94 million miles away. This variation affects seasons slightly, but not as much as the tilt of Earth's axis does. The tilt is why we have seasons. When the northern hemisphere tilts toward the sun, it's summer there. When it tilts away, it's winter. The distance matters less than the angle. From your current position, somewhere in interplanetary space, Earth's orbit is invisible. You can't see the path it traces. You'd have to watch for an entire year to see Earth complete one circuit around the sun. But you can imagine it, a flat disk, roughly circular, with Earth moving along its edge at 67,000 miles per hour. Fast enough to circle the planet's own equator in about 20 minutes. But in the scale of space, that speed is slow. It takes a full year to complete one orbit. The distances are so vast that even extreme speeds feel glacial. The sun's gravity extends far beyond the planets. Technically, it extends infinitely, just getting weaker with distance. But practically, there's a point where other stars' gravity becomes comparable. That point is roughly a light year or two from the sun. Beyond that, objects are influenced as much by neighboring stars as by the sun. This region, filled with icy comets, is called the Oort cloud. It's the outermost boundary of the solar system, the Sun's domain. Beyond that, you're in interstellar space, but we're nowhere near that boundary yet. You're still deep in the Sun's embrace. Its light still dominates. Its gravity still holds you. If you stopped moving sideways, you'd fall toward it. That fall would take months or years, depending on your starting distance, but it would be inevitable. The Sun pulls everything toward itself. Only sideways motion, orbital velocity, prevents collapse. Look at the Sun's surface. From this distance, you can't see details, but they're there. Sunspots, dark regions where magnetic fields suppress convection and lower the temperature. Solar flares, eruptions of energy that release as much power as billions of nuclear bombs in minutes. Coronal mass ejections, huge clouds of charged particles flung into space. The Sun isn't calm. It's violent, turbulent, constantly churning. The surface temperature is about 10,000 degrees Fahrenheit, hot enough to vaporize any known material. But the core is much hotter, around 27 million degrees. At that temperature, hydrogen nuclei slam together with enough force to overcome their electromagnetic repulsion and fuse into helium. This fusion releases energy according to Einstein's equation. A tiny amount of mass converts into a tremendous amount of energy. That's how stars shine. The Sun is middle-aged. It's a main sequence star, meaning it's in the stable phase of its life, where it fuses hydrogen into helium in its core. This phase lasts about 10 billion years for a star of the Sun's mass. The Sun is about halfway through. In another 5 billion years, the hydrogen in the core will run out. The core will contract and heat up. The outer layers will expand. The Sun will become a red giant, swelling to perhaps Earth's current orbit. Mercury and Venus will be swallowed. Earth might be too, or it might survive in a scorched, airless orbit around a bloated, dying star. Eventually, the Sun will shed its outer layers into space, creating a planetary nebula. The core will collapse into a white dwarf, a dense remnant about the size of Earth, but containing half the Sun's original mass. The white dwarf will cool over trillions of years, eventually becoming a black dwarf, a cold cinder floating in darkness. But this is so far in the future that the universe itself might not last that long in a form we'd recognize. For now, the Sun is stable. It's been stable for billions of years. It will remain stable for billions more. This stability is rare. Most stars vary. Some pulse. Some erupt. Some are binary systems where two stars orbit each other, creating complex interactions. The Sun is solitary and steady. That steadiness allowed life to develop on Earth. If the Sun varied significantly, Earth's climate would swing wildly. Life might not have survived. But from Earth's perspective, the Sun is more than a physical object. It's a symbol. Cultures have worshipped it. Mythologies have personified it. Calendars have been built around it. The Sun governs time, days, seasons, years. It governs agriculture, when to plant, when to harvest. It governs migration patterns in animals. It governs human mood. Sunlight affects serotonin levels. We are shaped by the Sun in ways we rarely acknowledge. Out here, away from Earth, the Sun loses some of that cultural weight. It's not a god. It's not a symbol. It's a star. A common type of star. There are billions of stars in the galaxy similar to the Sun. Some slightly larger, some slightly smaller, some hotter, some cooler. The Sun is unremarkable in the cosmic catalogue. A yellow dwarf star of spectral type G2V, average mass, average luminosity, average lifespan. But it's our star. the one that happened to have planets. The one that happened to have a planet at the right distance with the right conditions for life. From where you're floating, that planet is invisible, lost in the glare. A forgotten spark in the overwhelming presence of the star that made it possible. Earth doesn't matter to the sun. The sun would shine the same whether Earth existed or not. It's shone for millions of years before Earth formed. It will shine for billions of years after Earth is gone. The relationship is one-sided. Earth depends entirely on the sun. The sun doesn't notice Earth at all. This is a humbling thought. We live on a world that orbits a star that doesn't care. The sun gives us light and warmth, but not intentionally. It radiates energy in all directions because that's what stars do. Earth just happens to be in the path of some of that energy. If Earth moved, the sun wouldn't change. If Earth vanished, the sun wouldn't dim. Yet that indifference is also comforting. The sun's steadiness means we can rely on it. It will rise tomorrow. It will set tomorrow night. The seasons will continue. The sun doesn't play favorites. It doesn't punish or reward. It just exists, burning hydrogen, radiating light, anchoring the solar system with its gravity. From this distance, you can see the sun's influence on everything. The way planets orbit in the same plane because they formed from the same disk. The way their orbits are spaced, inner planets close together, outer planets farther apart. The way light dominates the inner system and fades in the outer system. The way heat shapes atmospheres, thick on Venus, thin on Mars, non-existent on Mercury. The sun created this structure. Its gravity gathered the material. Its heat drove volatile materials outward during the solar system's formation. Its radiation strips atmospheres from planets too small or too close to hold them. Its light powers photosynthesis on Earth, which produces oxygen, which enables complex life. The sun is the architect, even though it never intended to build anything. Look at the stars beyond the sun. Thousands of them visible even with the sun in your field of view. Each one a sun in its own right. Each one possibly surrounded by planets. Each one shining because it's fusing hydrogen into helium, just like our sun. Some of those stars are larger. Some produce more energy. Some will die in supernova explosions. Some will become black holes. The sun is average, but average is common. The universe is full of stars like the sun. And if the sun is common, then Earth might be common too. We don't know yet. We found thousands of planets around other stars. Some are rocky. Some orbit in the habitable zone where liquid water could exist. But we can't see details. We can't detect life remotely. Not yet. Maybe life is rare. Maybe we're alone. Or maybe the galaxy is full of planets with oceans and forests and creatures looking up at their own stars, wondering the same things. From here, those questions feel smaller. Earth is small. The sun is average. The solar system is one among billions. The Milky Way contains 200 billion stars. And there are 2 trillion galaxies in the observable universe. The numbers stop meaning anything after a while. They're just abstractions. But the feeling remains, the sense that we're part of something vast, and our part is tiny. The sun doesn't care, but we do. We care because we're alive. Because we're conscious. Because we can look at the sun and understand what it is. That understanding is rare, maybe unique. It's worth something, even if the universe doesn't notice. Hold on to this image. The sun burning in the darkness. Earth somewhere nearby, invisible, orbiting faithfully. The emptiness between. The light spreading outward forever. This is the solar system, a star and its debris. And somewhere in that debris, life appeared, not because the universe wanted it to, just because conditions allowed it. A spark in the overwhelming presence of a star that never notices. Keep moving outward, farther than you've ever imagined going, farther than humans have ever traveled. You're leaving the inner solar system behind. Jupiter is somewhere ahead, though you can't see it yet. The sun is behind you now, shrinking. This is where perspective changes in a way that can't be reversed. You've seen Earth disappear into the sun's glare. You've felt the emptiness between planets. But now something else happens. The sun itself begins to lose its dominance. Not because it's dimming, it's still extraordinarily bright, but because distance is doing what distance always does. It equalizes things. From Earth, the sun looks large because it's close. From 100 million miles away, it's smaller. From 1 billion miles away, it's smaller still. There's a point, somewhere far beyond the planets, where the sun stops being a disk and becomes a point. Just another star. Brighter than the others, but fundamentally the same. A dot of light in darkness. You're not there yet, but you're heading that way. And the journey reveals something profound about scale. The solar system that felt vast when you were crossing from Earth to Mars now feels compact. All the inner planets, Mercury, Venus, Earth, Mars, occupy a relatively small region. Jupiter orbits 5 times farther from the Sun than Earth does. Saturn orbits nearly 10 times farther. Uranus 20 times. Neptune 30 times. The distances are expanding exponentially, but from far enough away, they all collapse into a small region of space. Imagine standing on a hill overlooking a city. From the city center, the buildings seem spread out, but from the hill, the entire downtown fits in your field of vision. You can see the edges. The city that felt endless when you were walking its streets now looks contained. That's what's happening to the solar system as you pull back. It's not getting smaller, it's the same size it always was, but your perspective is shrinking it. Jupiter is the first of the gas giants. If you could see it from here, it would be the largest planet by far. 11 times Earth's diameter. More massive than all other planets combined. A swirling storm of hydrogen and helium with no solid surface. The Great Red Spot, a storm larger than Earth that's been raging for at least 300 years. Dozens of moons, including 4 large enough to be planets in their own right if they orbited the Sun directly. But Jupiter is far away. Even from where you are now, millions of miles beyond Mars, Jupiter is still farther. It's a bright point of light, yellowish-white, steady. It doesn't twinkle because there's no atmosphere to distort its light. From Earth, Jupiter is one of the brightest objects in the night sky. From here, it's the same, bright, but just a point. All that complexity, all those storms and moons, compressed into a single pixel. Saturn lies beyond Jupiter, the ringed planet. From Earth, through a telescope, Saturn is breathtaking. Delicate rings made of ice particles and rock, tilted at an angle, catching sunlight. But from here, Saturn is fainter than Jupiter, smaller, farther. The rings are invisible unless you have extraordinary instruments. It's just another point of light, slightly dimmer, slightly more yellow. Uranus and Neptune are barely visible even from here. They're so far out, so dim that they blend with background stars. Uranus is about 2 billion miles from the Sun. Neptune is about 3 billion. At those distances, the Sun provides very little warmth. These planets are cold, hostile, blue-green ice giants with atmospheres of hydrogen, helium, and methane, winds that reach supersonic speeds. But from your position, they're rumors, faint suggestions of light that you wouldn't notice unless you knew where to look. The sun is still the brightest thing you can see, but it's not overwhelming anymore. It's not flooding your vision. It's not washing out the stars. You can look at it directly, or you could if you were actually here, and it wouldn't blind you. It's still clearly the sun. Still a disk, though much smaller than from Earth. But it's becoming comparable to other bright stars. Sirius, if it were in your field of view, would be noticeably dimmer than the sun, but not absurdly so. The gap is closing. Keep going. Days pass. Weeks. Months, if you're moving at realistic speeds. You pass the orbit of Neptune. You're now 3 billion miles from the sun, 30 times farther than Earth. Light from the sun takes more than 4 hours to reach here. If someone on Earth tried to communicate with you, there'd be an 8-hour round-trip delay. You say hello. 4 hours later, they hear it. They respond. 4 hours later, you hear them. Conversation is impossible. Only scheduled transmissions work. From here, the sun is small, very small. If you held up a pinhead at arm's length, it would cover the sun. It's still bright, about as bright as the full moon appears from Earth, but it's no longer dominant. The sky is dark. Stars are sharp and clear. The Milky Way is a glowing band across the sky, more vivid than you've ever seen it because there's no light pollution, no atmosphere, nothing to soften it. Look back toward the inner solar system. You can't see the planets individually anymore. Maybe Jupiter is bright enough to pick out. Maybe. But Earth? Mars? Venus? Gone. Invisible. They're too small, too close to the sun, and their reflected light is too faint to register. The solar system, from here, is just the sun. A bright star with some invisible stuff orbiting it. This is the beginning of the shrinking. The point where the solar system stops being a place with distinct locations and becomes a single object, a star. From Earth, we think of the solar system as enormous. We measure it in astronomical units and talk about the vast distances between planets. But from far enough away, all those distances collapse. The space between Earth and Neptune, which is almost 3 billion miles, becomes irrelevant. They're both in the same tiny region of space surrounding the sun. Keep moving. You're entering the realm of the Kuiper Belt now, though you can't see it. The Kuiper Belt is a region beyond Neptune filled with icy bodies. Pluto orbits here. So do thousands of other objects, remnants from the solar system's formation. But they're dark, small, spread out over such vast distances that you'd never see them. You'd have to know exactly where to look and have powerful instruments. The sun continues to shrink. At this distance, maybe 40 or 50 AU from the sun, it's a very bright star, but clearly a star, a point. You can't see its disk anymore without magnification. It's lost the presence it had in the inner solar system. It's no longer the center of everything visually. It's just the brightest object among many. And as you keep going, farther into the outer reaches of the solar system, toward the Oort cloud, the sun dims. Not because it's producing less light. Because you're so far away that the light spreads thin. At 1000 AU, 1000 times Earth's distance from the sun is barely brighter than other stars. It's identifiable only because you know which one it is. The solar system, from this distance, is a star. That's all. Everything else is too faint or too small to see. The Oort cloud is theoretical. We've never directly observed it. But comets come from somewhere, and their orbits suggest a vast shell of icy objects surrounding the solar system. This shell extends perhaps a light year or more from the sun. Objects here orbit so slowly that a single orbit takes millions of years, They're barely bound to the sun. A passing star could disturb them, sending them inward toward the sun or outward into interstellar space. At this distance, the sun's gravity is weak but still present. You're still technically inside the solar system, but it doesn't feel like it. The sun is just a star. The planets are invisible. There's no sense of place, no landmarks. Just the general glow of the Milky Way and the scattered points of other stars. This is the edge, the boundary between the solar system and everything else. Not a hard boundary. There's no wall. Just a gradual transition. The sun's gravity fades. The solar wind, the stream of charged particles flowing from the sun, slows and mingles with the interstellar medium. The heliosphere, the bubble of solar influence, ends somewhere out here. But beyond this, you're in interstellar space, the realm between stars. Voyager 1, the most distant human-made object, crossed this boundary in 2012. It's now in interstellar space, more than 15 billion miles from the sun. From Voyager's perspective, the sun is a bright star, but not overwhelmingly so. The solar system has shrunk to a point. All the planets, all the moons, all the asteroids, everything is contained in a region that looks like a single star from that distance. Feel that shrinking, not as a calculation, but as a sensation. The world you knew, the solid ground, the sky, the ocean, became a sphere. The sphere became a pale blue dot. The dot became invisible. The sun that warmed that world became smaller. The solar system that contained that sun became a point. Everything collapsed inward, compressed by distance into something you could block with your thumb. And you're not even far yet. Not really. You've traveled billions of miles, but in cosmic terms, you've barely left home. The nearest star to the sun, Proxima Centauri, is more than 4 light-years away. In miles, that's about 25 trillion. Voyager 1, traveling at about 38,000 miles per hour, would take more than 70,000 years to reach it. The solar system is a tiny island in a vast ocean of emptiness. But from here, looking back, the solar system is a memory, a bright point of light that was once everything. The sun, which dominated your view for so long, is now just another star. The planets, which seemed so substantial, are gone. The Earth, where every human who has ever lived was born and died, is invisible. Not because it's not there, because distance has erased it. This is the feeling, not smallness exactly, more like insignificance. The solar system, which felt infinite from within, is finite from without, contained, bounded, small. And if the solar system is small, what does that make Earth? What does that make you? Don't answer yet. Because we're going farther. The sun is about to join Earth in the background. We're leaving the solar system behind and entering the galaxy. And the scale is about to change again in ways that make everything so far seem like a gentle warm-up. The sun is behind you now, a bright star among stars. Fading as you drift farther into the darkness between. You're in interstellar space now, the void between suns. This is where most of the galaxy exists, not in stars, but in the emptiness surrounding them. The nearest star to the sun is Proxima Centauri, part of a triple star system called Alpha Centauri. It's 4.24 light-years away. That means light, traveling at 186,000 miles per second, takes 4.24 years to cross the distance. Nothing travels faster than light. It's the universe's speed limit. So 4.24 light years is the closest another star can be, and that's still unfathomably far. In this darkness, stars are scattered like sand grains across a desert. From Earth, they look crowded. The night sky is full of them, but that's an illusion of projection. We see them all flattened onto a sphere, compressed into a two-dimensional view. In reality, they're separated by distances that would take human lifetimes to cross even at light speed. The sun is one grain of sand in that desert, and now that you're pulling away from it, you can start to see the desert's shape. Because stars aren't distributed randomly. They're part of a structure, a galaxy, the Milky Way. You can't see the galaxy's full shape yet. You're inside it. That's the problem with being inside something vast. You can only see the parts near you. It's like standing in a forest and trying to understand its shape. You see trees, but not the forest's outline. To see that, you'd need to rise above it. You'd need distance. But even from inside, you can sense the structure. Look around. Stars are everywhere, but they're not uniform. They cluster in a band across the sky, a glowing river of light. The Milky Way is seen from Earth, a pale stripe running from horizon to horizon on clear, dark nights. That band is the galaxy's disk seen edge-on from inside. The Milky Way is a spiral galaxy, a flat disk with arms spiraling outward from a central bulge. The disk is about 100,000 light-years across. The bulge at the center is denser, packed with older stars, and at its very core, a supermassive black hole 4 million times the Sun's mass. The spiral arms contain younger stars, gas clouds, and the birthplaces of new stars, nebulae, where gravity collapses clouds of hydrogen into glowing spheres. The Sun orbits within this disk, about halfway out from the center. It's in a minor arm called the Orion Spur between two major arms, Perseus and Sagittarius. The Sun moves through the galaxy at about 500,000 miles per hour. That sounds fast until you realize it takes about 230 million years to complete one orbit. The last time the Sun was at its current position in the galaxy, dinosaurs had just begun to appear on Earth. The next time it completes an orbit, who knows what Earth will look like? From your position now, drifting away from the Sun, the galaxy is starting to reveal itself. Not as a shape yet, you're not nearly far enough away for that, but as a distribution. Stars are denser in certain directions. The center of the galaxy, toward the constellation Sagittarius as seen from Earth, glows brighter. There are more stars there, older stars, red and yellow and packed close together. In other directions, stars are sparser. Toward the galaxy's edge, the density drops, the disk thins. Beyond the disk is the halo, a roughly spherical region containing globular clusters. These are tight balls of hundreds of thousands of stars orbiting the galaxy's center in elongated ellipses. They're ancient. Some of the oldest objects in the galaxy. Formed when the Milky Way was young, more than 12 billion years ago, but you can't see those details yet, not without instruments. From here, the Milky Way is still aglow. A concentration of light, a sense of density. The individual stars are points, scattered across your view. Some are bright. Some are faint. Their colors vary. Blue stars are young and hot. Red stars are old and cool. But mostly they're white. Tiny pinpricks against black. Keep moving, not toward anything specific. Just away. Away from the sun. Away from the solar system. Into the space between stars. This region is not empty. It's filled with the interstellar medium, gas and dust spread incredibly thin, roughly 1 atom per cubic centimeter on average. That's essentially vacuum by Earth standards. but across light years, it adds up. The interstellar medium contains mass. It absorbs light. It dims distant stars slightly. It glows faintly when radiation excites it. This medium is where new stars form. Gravity pulls gas into denser regions. Those regions collapse. As they collapse, they heat up. Eventually, the core gets hot enough to ignite fusion. A star is born. Around it, leftover material might form planets. The Sun formed this way 4.6 billion years ago. The Earth coalesced from debris around it. We're all made of recycled star material. The atoms in your body were forged in stars that died before the Sun was born. That's not poetic metaphor, it's literal. Hydrogen and helium formed in the Big Bang. Everything heavier, carbon, oxygen, nitrogen, iron, formed inside stars through fusion. When those stars died, they expelled those elements into space. Some through gentle solar winds, some through violent supernova explosions. That enriched gas mixed with the interstellar medium. New stars formed from it. Planets formed. Life arose. You exist because ancient stars died and scattered their contents across the galaxy. From here, you can see some of those stellar deaths. Supernova remnants glow in the distance. Expanding shells of gas, still hot from the explosion, visible across light years. The Crab Nebula, the Veil Nebula. Structures that were once stars, now dispersing back into the medium. In thousands of years, that gas will cool and mix with other gas. Eventually, it might collapse into new stars. The cycle continues. The galaxy is alive in this sense, not biologically, but dynamically. Stars are born. They shine. They die. Their remains form new stars. It's a slow cycle, playing out over millions and billions of years, but it's constant. The Milky Way has been doing this for more than 13 billion years. It will continue until the gas runs out or the galaxy merges with another. And mergers happen. Galaxies collide, not the stars themselves. Stars are so small and space is so empty that they rarely hit each other, but the galaxies pass through each other. Their gravity disrupts orbits, triggers star formation, reshapes structures. The Milky Way is currently colliding with a dwarf galaxy called the Sagittarius Dwarf. It's tearing the smaller galaxy apart, absorbing its stars into the Milky Way's halo. In a few billion years, the Milky Way will collide with Andromeda, the nearest large spiral galaxy. The two will merge into a single elliptical galaxy. The night sky from Earth, if Earth still exists, will look completely different. But that's the future. Right now, you're watching the Milky Way as it is. A swirling structure, a slow river of stars, 200 billion stars moving through space, held together by gravity, rotating around a common center. The scale is starting to overwhelm the mind. The solar system, which took billions of miles to cross, is invisible now. The Sun is one star among billions. Earth is a speck orbiting that star, too small and dark to see from even a light year away. Everything humans have ever done happened in a region of space too tiny to matter at this scale. Yet the galaxy feels almost gentle. It's not chaotic. It's structured, ordered. The spiral arms flow smoothly. The stars move in predictable orbits. There's a rhythm to it, a motion. The galaxy rotates, but not like a solid disk. The inner regions rotate faster than the outer regions. The spiral arms are not permanent features. They're density waves, regions where stars bunch up temporarily as they orbit. It's like traffic on a highway. Cars slow down in certain spots, creating a jam, then speed up again. The jam moves along the highway, even though the individual cars are moving at different speeds. The spiral arms work the same way. From inside the galaxy, this motion is imperceptible. The stars don't appear to move relative to each other over human lifetimes. The constellations look the same now as they did thousands of years ago. But over tens of thousands of years, they shift. The stars are moving, and eventually their positions change enough to distort the familiar patterns. Orion won't always look like a hunter. The Big Dipper won't always look like a dipper. The sky is slowly changing, but on timescales far beyond human perception. You're far enough now that the sun has faded significantly. It's still visible, but you'd need to know exactly where to look. It's one star among billions. There's nothing special about it from this distance. No indication that it has planets. No hint that one of those planets hosts life. It's just a yellow dwarf star, common in the galaxy, unremarkable in every way. Earth's location is unplaceable. Not because it doesn't exist. Because there's no way to point to it anymore. You could say it's near that particular star if you knew which star was the sun, but you couldn't point to Earth itself. It's too small. Too dark. It reflects such a tiny amount of light that even the most powerful telescopes couldn't pick it out from this distance. Earth has vanished not into the sun's glare this time, but into the galaxy's vastness. It's somewhere. But where is meaningless? The galaxy doesn't care about individual planets. Look at the sweep of stars. The glowing band of the galactic disk. The dense, bright core, the scattered outliers in the halo. This is home now. Not Earth. Not the solar system. The galaxy. This is the structure that contains everything you've ever known. Every star you've ever seen. Every constellation. Every nebula. All part of this one galaxy. The Milky Way. And it's beautiful in a way that's hard to articulate. Not because it's colorful or dramatic. Because it's vast and organized. Because it's ancient. Because it's indifferent to you, but allows you to exist within it. The galaxy doesn't notice life. It doesn't nurture it intentionally. Life is a side effect of chemistry and physics playing out on certain planets around certain stars. But the galaxy provides the stage, the raw materials. The time. Without the galaxy's structure, there'd be no heavy elements. Without heavy elements, no planets like Earth. Without Earth, no life. Without life, no one to look up and wonder. So the galaxy is home, even if it doesn't feel like it. Even if it's too large to grasp. Even if Earth is lost somewhere within it, unlocatable and invisible. The Milky Way is where you come from, where every photon that's ever reached human eyes originated, where every atom in your body was forged. It's a slow river of stars, flowing through space and time, carrying everything you know along with it. And now we're going to step back farther. Away from the Milky Way itself, into the darkness between galaxies. And the scale is about to change one more time. You're leaving the Milky Way. Not quickly. Galaxies are enormous, and crossing one takes millions of years even at light speed. But in this thought experiment, you're moving, drifting outward. The galaxy is shrinking behind you. At first, it barely changes. It's so large that distance doesn't seem to affect it. But gradually, imperceptibly, it becomes smaller. The individual stars blur together, the spiral arms lose definition. The bright core dims. Eventually, the Milky Way stops being a place you're inside and becomes an object you're observing. A spiral galaxy. Flat disk. Bright bulge. Spiral arms trailing outward. It's beautiful from here, delicate, glowing softly against the darkness. But you're not alone anymore. As you pull back, other objects come into view. Other galaxies. They're faint at first, smudges of light, hard to distinguish from stars. But as you move farther, they become clearer. They're not stars, they're galaxies. Each one containing billions of stars, each one a structure like the Milky Way. Some are spirals like ours. Some are ellipticals, smooth, featureless blobs of stars. Some are irregular, chaotic, and asymmetric. The nearest large galaxy to the Milky Way is Andromeda. It's about 2.5 million light-years away. From Earth, it's visible to the naked eye on dark nights, a fuzzy patch in the constellation Andromeda. But it's actually huge, larger than the Milky Way. Roughly 1 trillion stars compared to the Milky Way's 200 billion, and it's approaching. The Milky Way and Andromeda are moving toward each other, drawn by gravity. They'll collide in about 4 billion years. From your current position, maybe 1 million light-years from the Milky Way, Andromeda is visible. A spiral galaxy tilted at an angle, its disk glowing with the light of 1 trillion suns. It's not close, nothing is close at this scale, but it's nearby in cosmic terms. The Milky Way and Andromeda are part of a small group of galaxies called the Local Group. The Local Group contains about 80 galaxies. Most are small, dwarf galaxies with fewer than 1 billion stars. They orbit around the Milky Way and Andromeda like moons orbiting planets, the Large Magellanic Cloud and Small Magellanic Cloud, visible from Earth's southern hemisphere, are dwarf galaxies in the Local Group. They're satellites of the Milky Way, orbiting it, slowly being pulled apart by its gravity. But the Local Group is small. The galaxies are clustered in a region about 10 million light-years across. Beyond that, there's a gap, a void. For tens of millions of light-years, there are very few galaxies. Just emptiness. The Local Group is an island in a dark ocean. Keep pulling back. The Local Group shrinks. The individual galaxies blur into points of light. The Milky Way, which dominated your view a moment ago, is now just one speck among many. Andromeda is another speck. The distinction between them is fading. They're part of a group, and the group is becoming a single object. Around the Local Group, other groups and clusters come into view. The Virgo cluster is the nearest large cluster, about 54 million light-years away. It contains about 1,500 galaxies. Big ones, small ones, all bound together by gravity. The cluster is dense at the center, where giant elliptical galaxies dominate. These galaxies form through mergers, smaller galaxies colliding and combining over billions of years. They're old. Their stars are mostly red and yellow. They've used up the gas needed to form new stars. They're slowly fading. Farther out, there are more clusters. The Coma cluster, the Fornax cluster, each one containing hundreds or thousands of galaxies. These clusters are connected by filaments, long chains of galaxies stretching across hundreds of millions of light-years. Between the filaments are voids, vast regions with very few galaxies. The universe has structure at this scale. It's not uniform, it's foamy. Filaments and clusters surround empty spaces like bubbles in soap foam. This structure formed from tiny variations in density in the early universe. Regions that were slightly denser than average attracted more matter through gravity. Over billions of years, those regions grew. Matter flowed along filaments toward clusters. The voids expanded as matter drained out of them. The result is the cosmic web, a network of filaments and clusters spanning the observable universe. The Local Group is part of a larger structure called the Virgo supercluster. A supercluster is a collection of galaxy groups and clusters. The Virgo supercluster contains the Local Group, the Virgo cluster, and dozens of other groups and clusters. It's about 110 million light-years across. It contains tens of thousands of galaxies, and it's just one supercluster among millions. But even superclusters are not the largest structures. Recent observations suggest that the Virgo supercluster is part of something even bigger, Laniakea, a supercluster complex spanning 500 million light-years. Laniakea contains about 100,000 galaxies. It's defined by the motion of galaxies flowing toward a central gravitational basin. The Milky Way is on the outskirts of Laniakea, drifting toward its center along with everything else in the structure. From your position now, maybe 100 million light-years from the Milky Way, these structures are becoming visible, not as individual galaxies anymore. You're too far away for that, but as concentrations of light, glowing regions where galaxies cluster, dark regions where galaxies are sparse, the foamy structure of the universe revealing itself. The Milky Way is gone now, not destroyed, just unplaceable. You know it's part of the local group, which is part of the Virgo supercluster, which is part of Laniakea. But you can't point to it. It's too small. One galaxy among 100,000 in this region alone. It's lost in the crowd. Invisible. A single raindrop in an ocean. Earth, of course, is even more lost. It's a planet orbiting a star inside a galaxy, inside a group, inside a supercluster. Layers upon layers of structure, each one dwarfing the last. Earth's location is not just unplaceable, it's meaningless. At this scale, individual planets don't register. Even individual galaxies barely matter. Only the large-scale structure is visible. But this structure is calm. It's not violent or chaotic. It's organized, gentle. The galaxies drift along filaments like boats on slow rivers. They merge occasionally, creating bursts of star formation, but mostly they just move, orbiting, falling, pulled by gravity into denser regions. The motion is imperceptible. Galaxies move at hundreds of miles per second, but they're so far apart that their positions barely change over millions of years. The voids between the filaments are eerie. They're not completely empty. There are some galaxies even in voids, but they're sparse. Most of the universe's matter is concentrated in filaments and clusters. The voids are like deserts, quiet, dark, unchanged by the activity happening elsewhere. Light crosses these voids for hundreds of millions of years without encountering much of anything. And the light itself is strange at this scale. You're seeing galaxies not as they are now, but as they were when their light left them. That light has been traveling for millions or billions of years. The galaxy you're seeing 1 billion light years away, it looked like that 1 billion years ago. It might look completely different now. It might have merged with another galaxy. Its stars might have aged and died. But you won't know for another 1 billion years when the light showing those changes finally reaches you. This time, delay becomes more pronounced the farther you look. The most distant galaxies visible are seen as they were more than 13 billion years ago, when the universe was young. Those galaxies might not exist anymore, or they might have evolved into something unrecognizable. But their ancient light is only now reaching us, telling us what they were, not what they are. The universe is a museum of light. Every photon carries information about the past. The farther you look, the deeper into history you see. From this vantage point, far outside the Milky Way, you're seeing countless galaxies at countless different moments in time. Some are young and blue, actively forming stars. Some are old and red, their star forming days behind them. Some are colliding, creating spectacular bursts of light. Some are quiet and unchanged. It's a snapshot of cosmic evolution spread across space and time. The structures around you, The clusters, superclusters, filaments, voids are beautiful in their organization. They're drifting gently through space, not chaotic, not violent, just moving, existing. The universe is calm at this scale. It's only when you zoom in to galaxies, stars, planets that you find noise and activity in life. Out here, it's quiet, peaceful. A vast canvas painted with gentle brushstrokes of light. And now, for the final step. We're going to pull back one last time, to see the universe as a whole, to watch everything collapse into a single view, to understand, as much as minds like ours can, what it means to be part of something this